Recording started again. So we were on slide 61 in lecture 1. Going to head to the next slide, which is the idea of random slopes. So we were talking about time-invariant predictors, level 2 person characteristics as predictors, and they cannot have random slopes, is the short answer, because there's no higher level for them to be random over. So think of it this way, like if I have a blue group and a pink group here, and each of them is measured repeatedly over time. And if I have my x-axis as time here, I can draw a separate line, like for each of these people here. That's no problem. But if it's a level 2 predictor like group, they're in the same group every single occasion, then you can't draw a line through a dot. It's constant. You can't. I mean, it's not going to work. So because you can't draw a line through a dot, you can't have a random slope for a level 2 predictor in a 2-level model. Where you could, though, is if there were a level 3. So if I were looking at, like, say, gender differences in performance, it might be the case that girls and boys do differently. That slope can't be random unless I have, say, different classrooms. And then maybe the difference between boys and girls would differ across classrooms. Then it could have a random slope. But in these models without a higher level, time-invariant predictors can't. So we don't have to worry about that.
Would that mean you had then like different groups of women and different groups of men?
It would be, so if it were occasions within children within classrooms, let's say, then at level 2, I could look at the difference between boys and girls. And that would have a fixed effect for the gender difference in any one class. Then I could examine the extent to which that gender difference varies up by classroom. And in that story, gender slope could be random over level 3.
Yeah, because you have then multiple of the same gender because of the different classes.
Yes, exactly, because we'd have multiple girls and multiple boys, so it wouldn't be 2 points. It would be like clouds of points, or, vectors. I can't gesture with that, but I have a point in my head. So that is to say we don't have to worry about random effects for our time-invariant predictors. So, in terms of sources of variance, so the role of a time-invariant predictor is to explain the U variance that's going to be in its equation. That means that by themselves, they only reduce intercept variance, same as if they're involved in an interaction with another time-invariant predictor. But for cross-level interactions, though, that's where it gets tricky. And so this is what I want to show you a couple examples of. If I have, say, predictor 1 and predictor 2 multiplied by time as an interaction, then it's going to explain the time random slope variance if it's in the model. And if it's not in the model, it'll explain residual variance instead. Let me see here. Yeah, we'll do one more. In terms of R-square and multi-level models, this gets very tricky because there are like 37 kinds of R-squares that people have made for multi-level models, and some of them are the same and some of them aren't. There's 2 different kinds that I tend to favor. One is called pseudo R-square and one is called total R-square. Pseudo is the idea of a per pile reduction in variance. So of each of the separate variance components, my intercept pile, my slope pile, my residual pile, I can calculate how much of the variance was explained by a predictor. And that can tell you specifically, relative to each type of variation, how well your model performed. But in models that have a lot of variance components, that gets confusing to keep track of. And so total R-square is an alternative. And you already know this. Do you remember R-square in multiple linear regression? That idea? So there's 2 ways to interpret R-square in that context, and it works the same way. One is explain variance. The other is if I were to save y hat, my predicted outcome from the fixed effects, as a column in my data set, and I were to ask for a correlation of that predicted outcome with the real outcome, the square of that correlation is R-square. So I can do that in any linear model, whether it's single level, multi-level, or anything, because it's only based on the fixed effects. So I will show you in Elmer how to do pseudo R-square as well as total R-square. There's one more version that is relatively recent, which is a different way of calculating pseudo R-square so that it won't go negative. And there is an R package for that, although I did not include it in the examples that I have here. So R-square can be a little bit tricky with respect to that. So here's a sort of finished example, and then I'll show you another example that would have all of the steps actually using R. So this is from my regular longitudinal class. These are real data. So the story behind these data is 101 older adults, and they are measured on a speeded measure of response processing speed. Basically, response time is the outcome. So they had a task where there were 3 numbers above a line and 3 numbers below a line on a computer screen, and as fast as they can, they had to answer whether the numbers were the same below as above. So number matching, very quick task. And they did this task several times within an experimental session, and they had 6 sessions over a 2-week period. So the whole goal of the study was to measure practice effects, not aging, because you're not going to age over 2 weeks. Maybe you feel like you've aged in the 2 days that we have this workshop, but that's different. So these are the individual trajectories, real data from this sample. And on the whole, it looks like people are getting faster over time at this task. It takes them somewhere in the neighborhood of, say, 2,000 milliseconds to do this at first, and then they gradually get better, except for this person. They didn't know what was up, but they eventually figured it out and got better. So we're going to be modeling this type of trajectory, and in order to figure out what kind of family of models would be most useful, I outputted some baseline statistics. So here are 2 different trajectories, sort of the most complex version of the change over time on average and the simplest version. So if I had just an empty model where time is not in the model, then it would predict the same response time on average across time. So that's what this model says. If there were no change, this is what it would look like. The other line is what's known as a saturated means model, or the ANOVA model if I just treated time as a factor, where I would have 6 parameters to perfectly recreate the 6 means. Now I could stick with that, but it becomes less useful when I want to think about the idea of predicting individual differences in trajectories. I would rather have a function that summarizes this change over time than having 6 separate means. And so this type of function could be described in a bunch of different ways. The way that I picked was a quadratic function because it looks like the rate at which people are improving slows down as time goes on. Most of the improvement happens after the first time they do this task. They get much better, and then it sort of slows down after that. So this, for balanced data, is something that you can always directly estimate. For unbalanced data, you might have to round it into convenient intervals just to make a picture like this. Not to model it, but just to make a picture. So I'm going with quadratic. Same thing on the variance side. So the y-axis in this picture is variance in response time at each occasion. And the blue line here is the prediction from the empty model with a random intercept only. A random intercept says that variance is constant over time. And the right answer, so to speak, is from what I would call an unstructured model, where all the variances and covariances get to be estimated separately. And that's the black line. So this type of changing variance over time in one direction, that's a dead giveaway, that you have random slopes in there of some kind, because the variance is shrinking as people become more and more homogeneous as time goes on. So this is what we're modeling with the fixed effects, the change in average response time across sessions. What the random effects are trying to do is model the change in the variance across time, not the mean. Model for the means, fixed effects. Random effects, model for the variance. So I did a quadratic model that looks like this. So the outcome I'm modeling is response time. This is in a stacked data set where it's 1 row per occasion per person. So each person has 6 rows of data. And time is session minus 1, so that time 0 is the first time they do this task. And I have time and time squared, to form my quadratic trajectory. Because I have 3 beta placeholders at level 1, I have 3 level 2 equations, 1 for each. And they're each structured the same way, fixed part plus random part. So for beta 0, that's how each person gets their own intercept. And given the way that I've set up the model, gamma 0, 0 is my fixed intercept, which is going to be the expected outcome at time 0. And this is my random intercept for how far off each person's intercept is from the fixed. Then we have my linear slope. Given the quadratic, this is the linear slope at time 0 specifically on average. And then u1 is how far off each person's linear slope is. And then finally beta 2 is my quadratic term. I have a fixed quadratic, which is half the rate of acceleration or deceleration, and then u2 is how far off. So it's the same structure for all 3 of these things. And I note that you would need 4 occasions to fit this model at a minimum because you have 2 random slopes and an intercept. So chapter 6 of my book goes into more detail about why that is, but I'll just say you need 4 to do this. So let's throw in a predictor. One of the questions of interest in the study was to predict individual differences in improvement, and one of the predictors that we had was a measure of fluid intelligence, abstract reasoning. This is a variable that I think was a sum score of number correct, and I centered it near the average of 22, so that the reference point for the model would be somebody with average ability at time 0. So reasoning goes in at level 2. As a variable. Hey, stop that. And it gets an I because it's time constant, time invariant. Now note that I've got 3 different effects of reasoning. That's not a typo. I have 3 different effects of reasoning because I have 3 different ways that people differ from each other. So if we go through this row by row, this is my beta 0 intercept. That's going to be, the fixed intercept is the expected response time at time 0, given these predictors here, and also when reasoning equals 22, the reference point for where 0 is in the centered variable. Then gamma 01 is the main effect of reasoning, which is going to be the change in the intercept. So if we look at the subscripts, the pattern will hopefully make more sense than it did before. The first subscript is which beta we're talking about. So in this first row, they all start with 0 because this row is describing beta 0. Likewise, all the terms in the second row start with 1 because it's describing beta 1. The second subscript is the order of the predictor in the level 2 equation for that beta. So they all start with 0 for the fixed effects, then reasoning is the first predictor of beta 0. So if I added another variable in here, can you guess what the subscripts would be for it? If there was another one right here? 0, 2. And the next one? 0, 3. Yeah, we don't need coffee. We got this. It's just counting. So this effective reasoning adjusts the intercept specifically. Why do some people start out on this task better than others? Maybe it's because they have more fluid intelligence. Then U0 here is still the random intercept, but it has a different meaning. This is random intercept left over after controlling for reasoning. And I'm going to say leftover quite deliberately because a lot of books talk about these as level 2 residuals, and I find that confusing because level 1 is the residual. But when they say residual, they mean leftover. So this represents all the ways that people differ from each other in their intercepts after controlling for reasoning. So if reasoning matters in predicting the intercept, then this variance component that goes with this U0 should be smaller after including reasoning. So we can directly assess the effect size of reasoning as a predictor of the intercept by seeing how much did this tau squared U0 variance go down. Same idea as in regression, except there's 4 different variances we have to keep track of. 4 blue things. That's where the 4 comes from. Okay, with me so far? Yes?
I have a question related to the mutation.
Yes.
IoT modeling when we have two level 2 predictors, so item and person specific effects. And we would, so do you have a slide for the notation where I can look up in which pattern I should write this down? Because I'm wondering when I have an effect of person, then I would consider this index, or for the item another position. But when I have interaction effects, then I kind of failed to find a way to make the reader understand that it's in person item interaction effect that I'm looking at.
Yeah, so in that context, if the first subscript had to do with people things and the second subscript had to do with item things, then an interaction would be like this right here, where there's a number in both.
Okay. That sounds much easier than I normally think about. Yeah, I'm really working with those models, but yeah, thanks. Okay.
Yeah, if a fixed effect is both for a person and for an item, then I would interpret that as a person characteristic interacting with an item characteristic. In the same way that these two are actually interaction terms as well.
And so then I would have 3 indices, right? So if I have a response level, and a respondent, and an item, and then I would have put a 0 for the first, which is the actual response, or yeah, okay.
Yep. You were at my talk on Friday, I think.
Yeah, I wanted to have a look into the slides.
Yep, they're on my website.
Yeah, right.
So yes, because in the crossed items and persons, I have the exact same thing, although I have the setup for what you're talking about. I don't have any cross interactions in the model, but it's exactly what you said. Like the response is level 1, that has one subscript. Then you have a subscript for which item is which and which person is which. And if it's an interaction term of a person characteristic and an item characteristic, then it would have numbers in both places.
Okay. Yeah, thanks. That clarifies.
Yeah, it's parallel to this. It's just that this is only one level 1 and one level 1 and one level 2. Whereas if this was a random item model, then you would have 2 level 2s, which would take 3 subscripts altogether.
Yes.
Okay. Yes. Okay. Yes. Very nice segue, by the way, because now we're ready to talk interaction terms. So beta 1 then. This is how each person gets their own linear time slope. It starts with a fixed linear time slope. So this is conditional. Because time squared is in the model, this linear slope is specific to time 0. And because we have reasoning in this place, it's also specific to, this is a typo. What should that say here? 22, yes. I'd like to pretend that I put that there deliberately as a test, but no, I just screwed up. This should be 22 right here. So any typos, by the way, that I find, I will fix and repost the slides later. So if I'm on slide 69 and I've only found one typo so far, then I feel pretty good about that. So this is sort of my jumping off point for how the linear slope is formed. Then this right here is reasoning by time. It's not obvious from this notation system, but if you stick all these things into beta 1 and bring it up here, then each of these 3 terms multiplies time. So gamma 1, 1 is reasoning at level 2 multiplied by time at level 1. It's called a cross-level interaction because the predictors are at 2 different levels. So this you can think of as how the linear slope differs as a function of reasoning. Or you can think of it as how the effect of reasoning changes linearly over time. Either way works. And then this U1 is the random slope deviation, the leftover random slope after controlling for reasoning. And then in the last row we get the same pattern. We have the quadratic slope. This is conditional on reasoning because reasoning is here. It's not conditional on time 0 because the quadratic is the highest order in the model. And then 2, 1, this is actually a 3-way interaction term. It's reasoning by time squared. So it's how the quadratic slope differs as a function of reasoning. And then U2 is the quadratic slope variance that It's the idea that there is quadratic slope variance left. U2 specifically is the person-specific deviation. So I skipped a bunch of steps in getting to this model to get to the end point. But typically you would sort of go one at a time. Do I need fixed linear? And then do I need random linear? Do I need fixed quadratic? Do I need random quadratic? And then you can put in the effects of your time-invariant predictor. And we would have as many potentially different effects as we have u's in these level 2 equations. So putting it more condensed, it looks like this in a composite form. So the gamma 1 term, you can see a little bit more directly how it multiplies time here, and the 2 1 term multiplies by time squared. And so these two latter terms are what's known as cross-level interactions. Because they are supposed to explain the U variance that's in its line, we need to make sure that that U variance is part of the model if it needs to be there. So here's my solution from this particular example. Well, I've described the solution with a picture. So this is a pretty typical way to show results of time-invariant predictors. The level 1 axis is session. So time 0 is the first occasion right here. Reasoning 22 is the middle line. So this is like my reference growth curve, is this blue line. And then I picked high, I'm doing air quotes by the way for the recording, I'm doing high and low values of reasoning based on roughly plus or minus 1 standard deviation. So pink represents people with relatively low reasoning, purple represents people with relatively high. These are just examples. I did not cut up this variable. So the first 3 terms here in each of these, 1966 minus 120, 13, those 3 numbers form this blue line in the middle. At time 0, which is session 1, for somebody with reasoning 22 is my reference, they are predicted to take 1966 milliseconds to do this task. So almost 2 seconds right here. The minus 120 is my fixed linear slope. That is the rate of change at this point specifically. It's the slope of the tangent line to the curve right here. So they are improving at the rate of 120 milliseconds a session. Now what happens to it with the positive 13? Which pattern is this? It's either more positive, less positive, more negative, or less negative. Negative is one of them. Is it more or less, though? Yeah, the positive quadratic, it makes it less negative. It's slowing down. So it's minus 120 at this point. By the next session, the model predicts it to slow down by twice the quadratic. Twice. So by 26. So that means minus 120 plus 26 is the slope right here. And then plus another 26 plus another 26. So it's the slope, I can do it this way, there we go. Is this right? Okay. It's the slope that's slowing down. And eventually what's going to happen to it according to the model? You come back up the other side. Yeah, and you can kind of see that starting to happen at the end of the trajectory here. So this is what the model predicts. Okay, with me so far? All right, thumbs, excellent. So then we can talk about 3 different ways that reasoning is affecting the trajectory. People who are smarter start out faster. The purple, the distance between the lines right here at the intercept, that's what the minus 27 is doing. For every unit more reasoning you have, so I think for every additional question you get right, we start out lower by 27 milliseconds. That means faster. So this is an outcome in which lower is better because it's response speed. So that describes the vertical distance between these lines. So the actual distance would be minus 27 times 5 because these are 5 units apart in reasoning. Then the minus 3.6. So if my reference person in blue here is minus 20, what is reasoning doing to it? Is it making it more negative or less negative? These two numbers right here. Yeah, this is a more negative. So the purple person here with the higher reasoning, they have a steeper slope initially. Not by much, only by 3.6 milliseconds. And I don't care if it's significant for the point of the story. I'm just trying to get the numbers down. So people who have more reasoning are changing more initially. They have a steeper rate of improvement. There we go, this way. And then the quadratic. Their quadratic is more positive. We've got the two numbers together, which this is where the picture really helps. The more reasoning you have, the more your trajectory slows down. So there's more of a less negative. More or less negative. Perfectly clear, isn't it? So they're leveling off faster, essentially, is what's happening, but just by 1 millisecond, so not very much. So here's my summary of my results section. People with better reasoning started out faster, improved more initially, but had a greater rate of deceleration over time. So 3 different ways that reasoning affects the trajectory because I have 3 different sources of individual differences. And in fact, we can look at the pseudo R-square for each of these. Relative to the model without reasoning in it, adding reasoning accounted for 5% of the U0 variance, negative 0.006% of the U1 variance, and that's not a typo. That is the nature of pseudo R-square. Especially if you have very small effects, it can actually go up. Part of that is because of the collinearity between linear time and quadratic time. Do you think that time and time squared are going to be related to each other? Yeah, probably. So to that extent, it gets tricky to estimate separate variance components for linear and quadratic time when time is centered at the beginning like that. But it did explain about 2% of the quadratic variance. And it explained exactly 0 of the level 1 E variance that's left. Surprising or not surprising? Not surprising, I agree. Why is that? It did not predict it, that's right. Could it have by itself? By itself, it cannot. So conceptually, what does E variance represent? Level 1 residual within person variance here. Is it a between person thing or a within person thing? We'll go with multiple choice questions here. And feel free to read from the screen. Within persons. So E is, why are you off your line today? It can't be because of my reasoning, because you only measured reasoning once and it's a constant thing. So there's no way that reasoning by itself can explain time-specific variance. Reasoning by itself can only explain between-person differences in intercept, in linear slope, and in quadratic slope. So yeah, it should be 0 in this case. Question?
How did you know that it would be helpful to add the time square? Can we add it and not add it and then compare the models, or how do you know that we should do it exactly?
The exact process of how you would test whether time squared is needed depends on how you've estimated the model. You can always look at the p-value associated with the fixed effect walled test. So estimate divided by standard error treated as a t or a z. There's a p-value next to it you can always look at. The answer to whether you need the random quadratic, it's best answered with a likelihood ratio test. So -2 log likelihood difference between a model with it versus without it. If you're in residual maximum likelihood, though, you can only do that you can only compare models that have the same fixed effects and different random effects. So it's an empirical question as to whether you need time squared. The reason that I went down that road to begin with, though, is because of this picture right here. This to me looked like a quadratic function. So that's why I went in that direction, but then I would let the data decide what terms are actually needed or not. Because this implies that a fixed quadratic might be needed. Whether this change in variance maps onto a random quadratic is harder to tell. So yes, likelihood ratio tests for random effects. All right. I think we're... And here's how you would do this in 4 different packages. We're going to walk through some Elmer examples here in next. That'll be our next thing that we do. Okay, so playing reviewer 2 then. Should I have used a latent growth curve? Here's what it would look like in a structural equation model format instead, where I have 6 different response time boxes for my observed occasions. I have an intercept factor, a linear slope factor. So note the loadings here, 0 to 5 is what time as a predictor would be, and a quadratic slope factor going from time squared from 0 to 25. The intercepts of these factors, because they're now being predicted by reasoning, are the 3 fixed effects. So I've got the notation inside the circles. The random effect variances of the U's are the variances of these latent variables. And I've got my level 2 reasoning box out here, and I've labeled the 3 fixed effects that it has in the diagram. So should I have done it this way instead? The cons, no if I want residual maximum likelihood or denominator degrees of freedom. I will end up with greater type 1 error for small n without those things. I also need to have balanced time or definition variables. In this case, I had that. Why I might have done it this way is to do a latent basis model instead of a linear plus quadratic in terms of how the change was modeled. I also potentially would have more flexibility in how I want to have residual covariances among these things or different variances. In MLM software, it's generally all or nothing with respect to residual variance heterogeneity. And the biggest reason is if these boxes were actually circles. If I wanted to measure change in a latent variable, this is the way to do it. And here is some Mplus code that would estimate this model that way. The left-hand side is the random quadratic model, and the right-hand side is what it would look like as a latent basis model. So are you familiar with Mplus? Some are, some are not. So very briefly, there are 3 words in the Mplus vocabulary that you need to know. The word by, the word on, and the word with. That's it. By is how you set up factor loadings. So I am defining in this first piece right here a latent intercept factor measured by all of my 6 observed boxes with the factor loadings fixed at 1. That makes it an intercept. I am defining a linear slope latent factor by fixing the loadings at the values of time centered such that session 1 is 0. I'm defining a quadratic factor with the values of time squared. In Mplus syntax, when you list a variable inside brackets, you are asking about its mean or its intercept. When you list a variable by itself, you are asking about its variance or its residual variance. And if you have with, that's how you set up a covariance. So this part of it so far defines my fixed and random effects and their covariances. In the original variables here in brackets, that's fixing their fixed intercepts to 0. And by listing the variances of the level 1 outcomes and referring to them all as one word, I am constraining them to be equal. The green text are comments, by the way. And then the word on is defining a regression, and it's y on x. So this one line of code is setting up the 3 fixed effects of reasoning, predicting the intercept, linear, and quadratic. the difference on the right-hand side is this part right here. Do you see the stars? Those are estimated loadings. So this is a latent basis model. And I have the loadings in here, what they were estimated to be. So at time 1, I fixed the loading to 0. The next loading for RT1 here at the second occasion was estimated as 0.57. So another way to say that is 57% of the total change had happened by session 2. Then the next one was 76% of the change, 90% of the change, and then 97% of the change. So it defines a nonlinear shape that's empirically based. And it takes only one latent variable to do it instead of 2, which can make it more convenient to use that as a predictor or outcome of other things. The rest of the code is then the same, except that I'm calling this slope rather than linear, because I don't know what word you would call it, I just know it's a slope. Here's Lavon code to do the same thing. It's all green, which is one of my pet peeves of the way that we do this. So we have equal squiggle as how I set up the factor loadings. Squiggle by itself as how we do the intercepts if it's squiggle 1. These are regressions, I believe, otherwise. Double squiggle to refer to variances or residual variances. And squiggle with a different word at the end as a covariance. Then we fix the intercepts to 0, and we use the same label for all of the residual variances to hold them equal across time. And then the last squiggle then are the fixed effects of reasoning. The latent basis version worked out to be exactly the same, where we let the factor loadings be estimated instead of fixed to the values of time over here. Ta-da! Should I have used a multi-level SEM? No. That's the short answer. We don't require balanced time, that's not a problem here, but there's really no benefit to doing it this way. The only benefit would possibly be if we were using latent variables and we wanted to look at growth in latent variables instead. So that's an easy case. But this is what the syntax would look like in Mplus to do it as a multi-level SEM. It defines a level 1 model specifically as a within and a level 2 model specifically as a between. Lavon does have multi-level SEM, but it's much more limited. In particular, it doesn't have random slopes. And so I can't really use it for anything that I want to do with an example. All right. 358. How are we doing? Thumbs up. We're still here. We're hanging in here. My voice is going, but I'm hanging in there. Any questions at this point? Not just so far, but at this point. There, get out of there. Okay, do you want to see an example with R? Let's do that. Let's change gears. I'm going to